You trust Einstein because he was right about big things: relativity, space-time, mass, and energy. But being right about one thing doesn't make you right about everything. And Einstein's deepest conviction, his most passionate belief, the idea he defended until his death, was false. Provably false. The universe proved it. Not through argument, through measurement, through cold, repeatable experiments that any competent physicist can run today. Einstein believed reality was deterministic, predictable, mechanical, a clockwork universe where every effect has a local cause and nothing happens without a reason you can trace. He believed particles had definite properties even when you weren't looking. He believed the universe made sense. He was wrong. Quantum mechanics says otherwise. And Einstein spent 30 years trying to prove quantum mechanics was incomplete, a temporary approximation, a placeholder for deeper truth. He failed. Imagine you are Einstein in 1935. You have already revolutionized physics. Relativity is proven. Time bends. Space curves. You understand gravity better than anyone alive. But something is gnawing at you. A new theory called quantum mechanics is gaining ground, and it makes you furious because it says something you cannot accept. It says reality is random. Here's the thought experiment Einstein actually constructed. Take two particles. Entangle them in the laboratory so their properties are correlated. Now separate them. Send one particle to a detector on your left. Send the other particle to a detector on your right. Place these detectors across the room or across the galaxy. Distance doesn't matter for this argument. Now measure the particle on the left. You find it spinning clockwise. Instantly, without waiting, without sending any signal, you know the particle on the right is spinning counterclockwise. The correlation is perfect every time. Measure left, predict right. Measure up, predict down. Einstein said this is obvious. The particles had those properties all along. They were predetermined from the moment you created the pair. You just revealed what was already there. Like opening two envelopes that both contain matching lottery numbers. Opening the first envelope doesn't cause the second envelope to suddenly generate a number. The numbers were already written. You just didn't know them yet. This is local realism. Objects have properties independent of measurement. Causes are local. Information doesn't travel faster than light. The universe is a machine with gears and springs. Hidden, perhaps. Invisible, maybe. But real. Predetermined. Knowable in principle. But quantum mechanics said no. Quantum mechanics claimed the particles didn't have those properties until you measured them. The act of measurement on the left particle instantaneously forced the right particle to take the opposite value. Not because information traveled between them, but because they were part of a single quantum system. Measurement here collapsed the wave function there, instantly, across any distance. Einstein called this spooky action at a distance. He meant it as an insult. It violated everything he believed about causality, locality, and the structure of reality. How could measurement here affect reality, there without any signal passing between them? How could particles lack definite properties until you looked? How could reality be probabilistic at its core, not just in our knowledge, but in its actual existence? He wrote that God does not play dice with the universe. This wasn't a religious statement. Einstein's God was Spinoza's God, the God of natural law, order, predictability, elegance, a clockwork cosmos that runs on rules, not randomness. The idea that a particle could genuinely have no spin until you measured it, that the universe could be fundamentally uncertain, violated his deepest intuition about how reality must work. So Einstein insisted there must be hidden variables, deeper properties we couldn't measure yet, a complete theory beneath quantum mechanics that would restore determinism and locality. The particles knew their spins all along. We just hadn't found the right equations to predict them. For Einstein, quantum mechanics wasn't wrong. It was incomplete, a useful approximation, a placeholder. Something better, something deterministic, something sensible had to exist underneath. He spent 3 decades searching for it. Here's what quantum mechanics actually says. And this is where Einstein's intuition hits a wall it cannot climb. In quantum mechanics, particles do not have definite properties until you measure them. This is not a statement about ignorance. This is not us admitting we don't know which envelope contains which number. This is the claim that the number doesn't exist until you open the envelope. The particle doesn't have a spin. It doesn't have a position. It doesn't have a momentum. These properties are not hidden. They are not predetermined. They are not waiting to be discovered. They do not exist. What exists instead is a superposition, a mathematical object that contains all possible outcomes simultaneously. The particle is spinning clockwise and counterclockwise at the same time. Not in the sense that we don't know which. In the sense that both are equally real until measurement forces the system to pick one. When you measure the particle, the superposition collapses. The wave function, which described all possibilities, instantaneously reduces to a single outcome. You get clockwise or counterclockwise, up or down, here or there. But before measurement, the particle genuinely occupied all of those states. You've probably heard of Schrödinger's cat. The cat in the box that is both alive and dead until you open the lid. That thought experiment was designed to show how absurd this interpretation sounds. Schrödinger was on Einstein's side. He wanted to demonstrate that quantum mechanics, taken seriously, leads to ridiculous conclusions. A cat cannot be both alive and dead. That's nonsense, but the math works. The experiments confirm it. The cat, at the quantum level, genuinely is in superposition. Alive and dead. Both. Neither. Until measurement. This is the Copenhagen interpretation. Shut up and calculate. Don't ask what the wave function is. Don't ask what's really happening between measurements. The math predicts what you will measure. That's all physics can tell you. That's all physics should tell you. Einstein hated this. He called it incomplete. A refusal to do the hard work of finding the real mechanism underneath. He believed quantum mechanics was like thermodynamics before we discovered atoms. Useful, accurate, but not fundamental. Underneath the probabilities, there had to be definite particles with definite properties obeying definite laws. But there's another problem. Heisenberg's uncertainty principle. You cannot measure both the position and momentum of a particle with arbitrary precision. The more accurately you know where it is, the less accurately you can know how fast it's moving. This isn't a limitation of your measuring tools. This is a property of reality. The particle doesn't have a precise position and a precise momentum simultaneously. Not because we can't measure both, because both don't exist at the same time. Measuring one destroys information about the other. The act of measurement itself changes the system. So when Einstein imagined particles with hidden variables, with predetermined spins and positions and momenta written into their internal structure, quantum mechanics said no. Reality doesn't work that way. The universe runs on probability, on intrinsic randomness, on measurements that create outcomes rather than revealing them. Dice that don't show a number until you look. And even then, the number wasn't waiting on the hidden face. It materialized the instant your eyes made contact. This is not philosophy. This is measurable physics. The equations predict exact probabilities. The experiments confirm those probabilities, down to absurd decimal places. Quantum mechanics is the most precisely tested theory in the history of science. It works. But does that mean Einstein was wrong? Could there still be hidden variables? Could particles still have predetermined properties that we simply can't access? For 30 years, this was just an argument. Einstein said hidden variables must exist. Bohr said they don't. No one could design an experiment to settle it. Then, in 1964, a physicist named John Bell figured out how to turn philosophy into math. Let's talk about entanglement. Forget what you've heard from pop science articles about quantum telepathy or cosmic consciousness or particles that know what their twins are doing. That's mysticism dressed up as physics. Entanglement is not magic. It's a measurement correlation phenomenon. And it's the perfect test case for Einstein versus quantum mechanics. Here's what actually happens in a laboratory. You create a pair of particles in such a way that their properties are correlated. Entangled. You can do this with photons, electrons, atoms. The specific particle doesn't matter. What matters is the correlation. Now, you separate them. Send one particle to a detector on the left side of the room. Send the other to a detector on the right side. You can separate them by a meter. You can separate them by a light year. Distance is irrelevant to this phenomenon. The correlation persists. Measure the left particle. You find it has spin up. Instantly, without any delay, you know the right particle has spin down. Measure left particle polarized vertically. Right particle is polarized horizontally. Every time. Perfect correlation. No exceptions. Einstein's explanation was simple. The particles had those values all along. When you created the entangled pair, you predetermined their properties. Left particle was always going to be spin up. Right particle was always going to be spin down. You just didn't know which was which until you measured. The measurement revealed information that already existed. Think of it like gloves. You put a left glove in one box and a right glove in another box. You ship the boxes to opposite ends of the galaxy. Someone opens the box on the left and finds a left glove. They instantly know the other box contains a right glove. That knowledge is instant. But nothing spooky happened. The gloves were always left and right. You just found out which was which. Hidden variables, predetermined values, written into the particles when they were created. The universe as a deterministic machine where measurement reveals, but doesn't create, reality. Quantum mechanics said no. The particles don't have definite spins until you measure them. Both particles exist in superposition. Spin up and spin down simultaneously. When you measure the left particle, you collapse its wave function. And instantaneously, the right particle's wave function collapses too. Not because a signal traveled between them, but because they're part of a single quantum system. Entangled. Measurement here forces a definite outcome there. This isn't communication. You can't use entanglement to send messages faster than light. When you measure the left particle, you get a random result. Spin up or spin down. 50 to 50. You can't control which outcome you get, so you can't encode information. The person measuring the right particle also gets a random result. It's only when you compare the results later, using normal slower-than-light communication, that you discover the correlation. But the correlation is real, and it's instant. Measure here, and something happens there. No time delay, no signal, no mechanism. The universe doesn't respect distance for this phenomenon. Separate the particles by a millimeter or a megaparsec. The correlation is identical, instantaneous, perfect. So who's right? Einstein or quantum mechanics? Do particles have hidden properties all along, like predetermined gloves and boxes? Or does measurement here genuinely affect reality there through some non-local wave function collapse? For decades, this was pure philosophy. Einstein said hidden variables. Bohr said wave function collapse. They argued in conferences and journals, but no one could design an experiment to settle it. Both explanations predicted the same experimental results: perfect correlations. There was no way to tell which interpretation was correct until Bell. In 1964, a physicist named John Bell published a paper that changed everything. Not because he did a new experiment, not because he discovered a new particle, because he figured out how to turn a philosophical argument into a testable prediction. Bell asked a simple question. If Einstein is right and hidden variables exist, if particles really do have predetermined properties written into them from the moment of creation, what must be mathematically true about the correlations we measure? He proved that hidden variables impose limits, constraints. If particles carry predetermined instructions, if they're like gloves and boxes with fixed identities, then the correlations you measure between entangled particles cannot exceed a certain value. There's a ceiling, a maximum correlation strength that hidden variable theories cannot surpass. This ceiling is called Bell's inequality. It's a mathematical boundary. If your measurements stay below this boundary, hidden variables could exist. Einstein could be right. But if your measurements violate the inequality, if correlations exceed the limit, then hidden variables are impossible. The particles cannot have predetermined properties. And here's the kicker. Quantum mechanics predicts violations. The theory predicts correlations stronger than Bell's inequality allows. Correlations that should be impossible if particles have definite properties before measurement. Let's make this concrete. Imagine 3 coins. If the coins are predetermined, if they already show heads or tails before you look, there are limits to how often they can match when you flip pairs of them. You can calculate the maximum correlation mathematically. It comes from basic probability. But if the coins don't have definite faces until you look, if the act of looking forces them to pick heads or tails, then the correlations can be stronger. You can get matching results more often than predetermined coins allow. Bell proved this rigorously. He showed that any theory based on local hidden variables, any theory where particles have definite properties and influences travel at or below the speed of light, must satisfy his inequality. The correlations are bounded, capped, limited by the mathematics of predetermined values. Quantum mechanics violates the inequality. The theory predicts correlations that exceed Bell's limit, not by a little, by enough that you can measure the difference in a laboratory. This means you have a test, a real physical experiment that distinguishes between Einstein's worldview and quantum mechanics. You create entangled particles. You measure correlations. You calculate whether those correlations obey or violate Bell's inequality. If they obey the inequality, Einstein was right. Hidden variables exist. Particles have properties all along. The universe is local and deterministic. If they violate the inequality, quantum mechanics wins. Particles don't have properties until measured. The universe is non-local. Measurement here affects reality there, instantly. Before Bell, this was metaphysics. Philosophers arguing over coffee about the nature of reality. After Bell, it became physics. A question you could settle with photon detectors and correlation counters and statistics. Bell gave physicists the tool they needed. He turned what should reality be like into what does reality actually do. He made Einstein's intuition testable. And once something is testable, the universe gets to vote. This is not philosophy dressed up as science. This is science doing what science does best. Taking abstract questions and forcing them into the court of experiment. Bell's theorem is pure logic. If hidden variables, then correlations are limited. If quantum mechanics, then correlations can exceed the limit. Measure the correlations. See which prediction matches reality. The math is airtight. The logic is unassailable. The only question left was experimental. Do the measurements obey Bell's inequality or violate it? Bell had given the world a way to test reality itself. Now physicists needed to build the experiments, create the entangled particles, measure the correlations, count the statistics. If quantum mechanics was right, the measurements would violate Bell's inequality. If Einstein was right, they wouldn't. The universe was about to tell us which one was wrong. The experiments began in the 1970s. Physicists finally had the tools to test Bell's inequality, to measure correlations between entangled particles with enough precision to distinguish Einstein from quantum mechanics. The first major test came in 1972. Stuart Friedman and John Clauser at Berkeley created pairs of entangled photons, light particles. They measured the polarization of these photons at different angles: vertical, horizontal, diagonal. They counted how often the measurements correlated, how often measuring one photon vertically meant the other was horizontal, how often they matched or didn't match at different angle combinations. Then they calculated. Did the correlations obey Bell's inequality or violate it? They violated it. The correlations were stronger than hidden variables allow, not marginally, not within experimental error. Clearly, quantum mechanics predicted violations, and that's exactly what the measurements showed. Einstein's hidden variables would have produced weaker correlations. The data didn't match that prediction. They matched quantum mechanics. But one experiment isn't enough. Maybe there was a flaw. Maybe the setup had a loophole. So physicists kept testing. In 1982, Alain Aspect in France ran a more sophisticated version. He closed some of the potential loopholes. He made the measurements faster, changed detector angles while the photons were already in flight. No hidden communication between the detectors could explain the results. Same outcome. Violations of Bell's inequality. Stronger correlations than Einstein's local realism allows. Every experiment since has confirmed the same result. Different labs, different countries, different techniques, entangled photons, entangled atoms, entangled ions. The details change, but the verdict doesn't. Quantum mechanics wins every time. The correlations violate Bell's inequality, not by a little, by amounts that are statistically undeniable. Thousands of measurements, millions of particle pairs. The pattern is clear. And it's not the pattern Einstein predicted. For decades, skeptics could argue there were loopholes. Maybe information leaked between detectors. Maybe the choice of which measurement to make wasn't truly random. Maybe the detectors weren't efficient enough, and you were only seeing a biased sample of particles. Each criticism was legitimate. Each loophole was theoretically possible. So physicists closed them, one by one. In 2015, 3 independent experiments achieved what's called loophole-free tests of Bell's inequality. They separated detectors by enough distance that no information could travel between them during measurement. They made measurement choices random and fast. They detected nearly every particle. No escape routes left. All 3 experiments violated Bell's inequality, quantum mechanics, non-locality. The universe doesn't care about Einstein's objections. In 2022, the Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger for this work, for proving experimentally that the universe is non-local, that Einstein was wrong about hidden variables, that quantum mechanics correctly describes reality. This is not interpretation. This is measurement. Cold, repeatable, undeniable measurement. You can run these experiments yourself if you have the equipment. The protocols are published. The math is public. Any competent lab can verify the results. The universe has spoken. Entangled particles do not have predetermined properties. Measurement here does affect measurement there. Instantly, regardless of distance. Local hidden variables cannot exist. Not unless they conspire faster than light to fake quantum correlations, which would require the very non-locality Einstein was trying to avoid. Einstein lost. Quantum mechanics won. The experiments are clear. The statistics are overwhelming. The universe is non-local. But what does that actually mean? Non-locality means measurement here affects measurement there. Instantly, across any distance. No signal travels. No information is transmitted. But the correlation is real. This isn't some quirk of laboratory equipment. This isn't an approximation that breaks down at larger scales. This is how the universe actually works at the most fundamental level we can measure. The universe is not made of separate, independent objects. That's the illusion your biology wants you to believe. You look at a chair and a table, and you think they're distinct things, occupying different regions of space with their own independent properties. You think if something happens to the chair, it doesn't immediately affect the table unless a signal travels between them. A push, a sound wave, a beam of light. Causality respects distance. Influences propagate. Information takes time to cross space. Wrong. At the quantum level, entangled particles are not separate objects. They're parts of a single quantum system. Measure one, and you don't just learn about the other. You force the other into a definite state, instantaneously. Not because a signal traveled faster than light, but because the two particles were never truly separate in the first place. The correlation isn't explained by hidden communication. It's explained by abandoning the idea that these are two distinct objects with independent properties. They're one system, spread across space, but still one. This is what Einstein called spooky action at a distance. He was right to find it spooky. It violates every intuition you have about how reality should work. Objects should be localized. Properties should be intrinsic. Measuring something over here shouldn't immediately change something over there without any mechanism connecting them. But that's exactly what happens. Measure the left particle's spin, and the right particle's spin becomes definite, instantly. even if they're separated by light years, even if there's no possible way for information to have traveled between them in the time between creation and measurement. You cannot think of particles as separate objects with predetermined states. Not anymore. The experiments destroy that picture. You have to abandon something, either locality or realism. You can't keep both. Locality says influences travel at or below the speed of light. Things only affect their immediate neighbors. Causes are local. Realism says objects have definite properties independent of measurement. The moon is there even when you're not looking. Particles have spins and positions and momenta whether you measure them or not. Bell's theorem and the experiments that followed prove you cannot have both. At least one must go. The universe forces you to choose. Most physicists choose to abandon realism. They accept that properties don't exist until measured. The particles genuinely don't have spins until you measure them. Measurement creates reality, not reveals it. This preserves locality in a technical sense. No information travels faster than light, but it destroys the intuitive picture of an objective reality existing independent of observation. Some physicists try to keep realism and abandon locality. They accept that particles have definite properties all along, but those properties are determined by faster-than-light influences, hidden variables that coordinate across space instantly. But this requires exactly the spooky action Einstein was trying to avoid. Either way, your intuition loses. Either reality doesn't exist until you measure it, or reality is threaded together by instantaneous, non-local connections. Pick your poison. Both taste wrong. This isn't a quirk of particles. This is reality. The universe at its foundation is non-local. Distance doesn't mean what you think it means. Separation is less fundamental than connection. Objects aren't independent. The whole is more real than the parts. Einstein couldn't accept it. But the universe doesn't care what Einstein accepts. It doesn't care what you accept. If the universe is non-local, then what does that mean for everything else we thought we understood about reality? Start with the block universe. Einstein's own theory of relativity suggested that past, present, and future all exist simultaneously. Time is a dimension, like space. The universe is a four-dimensional structure where every event, from the Big Bang to the end of everything, is laid out like a landscape. You don't move through time. You exist at every moment of your life simultaneously. Your consciousness just experiences those moments sequentially. Entanglement makes this picture even more compelling. If two particles separated by light years can be instantaneously correlated, if measurement here forces a definite outcome there with no time delay, then the universe must already contain both events. The measurement on the left and the correlated result on the right. Both moments exist in the structure of space-time. Entanglement connects them, not through time, not through space, through the deeper fabric that underlies both. Remember that Einstein wanted to preserve now. He wanted a universal present moment that slices across the entire universe. Everyone could agree on what's happening right now, even if they disagreed about times measured on clocks. But relativity already destroyed that. Your now and my now are different if we're moving at different speeds. There's no universal simultaneity. Entanglement makes it worse. Measurements on entangled particles are correlated even when they're separated in time. You can measure one particle now and the other particle later, and the correlation still holds. The later measurement's outcome depends on the earlier measurement even though there's no causal chain connecting them in the traditional sense. Time doesn't protect you. Distance doesn't protect you. The universe is threaded together by correlations that ignore both. Now you might ask about free will. If the universe is this interconnected block of predetermined events, do you have any freedom? And here's where it gets truly strange. The block universe suggests everything is already laid out. Your choices, your decisions, your entire life. It's all there in the four-dimensional structure. Determinism wins. But quantum mechanics says no. Outcomes are genuinely random. When you measure a particle, you get an unpredictable result. Not unpredictable because you lack information. Unpredictable because the universe itself hasn't decided yet. Randomness is fundamental. So which is it? Deterministic block universe or quantum randomness? Both. The universe is deterministic in the sense that the entire structure exists. The block is real. But it's not locally deterministic. You can't predict the future by looking at the present and applying laws. Because the laws include genuine randomness. The future is fixed. But it's not computable from the past. Einstein wanted a clockwork cosmos, local interactions, predictable cause and effect. Determinism, you could trace step by step. Instead, he got a universe that's both predetermined and random. A block structure laced with quantum uncertainty. The worst of both worlds, or the best, depending on your philosophy. And here's Einstein's tragedy. He was right about relativity. Space and time are united. The universe is a geometric structure. His equations are still correct. They still describe how gravity bends space-time, how clocks slow down, how the cosmos expands. But he was wrong about quantum mechanics, and you can't separate them. Quantum mechanics and relativity are both true. Both describe the same universe. When you try to understand how they fit together, you get something stranger than either theory alone. Black holes, where quantum effects meet extreme gravity. Hawking radiation. The possible breakdown of space-time itself at the quantum scale. Questions about the beginning of the universe that might not even make sense because time itself is a quantum phenomenon. Einstein helped build both theories, relativity and quantum mechanics, and he lived to see them contradict his deepest beliefs about how reality should work. So Einstein was wrong. Not about everything. Not about relativity, or gravity, or the structure of space-time. He was right about those. Brilliantly, permanently right. But he was wrong about quantum mechanics. And he knew the experiments contradicted him. He saw the data. He understood the math. And he still couldn't accept it. This wasn't stupidity. This was something else. Einstein was fighting for a comprehensible universe, a cosmos that made sense to human intuition, where objects had properties, where causes were local, where God didn't play dice. He wanted reality to be elegant, deterministic, knowable in the way a clockwork mechanism is knowable. He couldn't let go of that vision, even when the experiments said otherwise. Throughout his career, Einstein had a rule. If theory contradicts experiment, theory loses. He said this explicitly. He meant it for relativity. Mercury's orbit didn't match Newton's predictions, so Newton's theory needed modification. Starlight bent around the sun during the 1919 eclipse exactly as Einstein predicted. Experiment confirmed relativity. Einstein trusted measurement. But with quantum mechanics, he made an exception. Not because the experiments were wrong. They weren't. The measurements were precise. repeatable, undeniable. He made an exception because he couldn't emotionally accept what the experiments were telling him. That's the lesson. Not about Einstein, about certainty itself. Even the greatest mind of the 20th century hit the wall of biology. Your intuition, no matter how refined, no matter how successful in other domains, is still just a survival tool. It evolved to help you catch food and avoid predators and predict where the rock will land. It did not evolve to understand quantum entanglement or the structure of space-time. When reality contradicts your deepest beliefs, when experiments demolish your intuitions, when the universe refuses to make sense in the way you need it to make sense, you have a choice. You can be like Einstein and insist reality must be wrong. Or you can accept that you are a biological machine trying to understand non-biological rules. The fact that we can do this at all is the wonder. We are made of meat and electricity. We evolved in trees and savannas to throw spears and find berries. And somehow, we figured out that the universe is non-local, that particles don't have properties until measured. That time is a dimension. That reality is stranger than any human mind naturally grasps. Einstein couldn't visualize quantum mechanics. Neither can you. Neither can anyone. We can do the math. We can run the experiments. We can make predictions and test them. But we cannot picture it. Our brains don't have the software. And that's fine. The universe doesn't owe you comfort. It doesn't owe you intuition. It doesn't owe you a reality that makes sense when you close your eyes and imagine it. Einstein was wrong. And that's the most beautiful proof that truth doesn't bend to genius.